So today's class, we are going to discuss about the comparisons between block diagram and signal flow graph. And one more problem we are going to solve on based on um, signal flow graph and Mason's gain formula. Afterwards, we'll introduce the time response analysis, the new chapter, the second chapter we are going to start today. So before going to the second chapter, so let us see. So comparisons between signal flow graph and block diagram method. So these are the comparisons. Please note down. So block diagram is a pictorial representation of the functions performed by each component and of the flow of signals. So it is a pictorial representation, same thing. In case of signal flow graph, it is a graphical representation of a relation between the variables of set of linear algebraic equations written in the form of cause and effect. So once from the mathematical model, if we write in cause and effect form, directly we can represent the variables, relation between the variables. Okay, so in graphical form. So that is signal flow graph representation. It is a pictorial representation. So both are pictorial representations only, but so it is graphical way of representation only with a straight lines, branches and nodes. We can represent a signal flow graph, whereas in block diagram, so again, each and every transfer function is represented with a block, and input signal is represented by arrow. Similarly, whatever be the output coming from the block, so it is represented by one more arrow. Okay, so input, output, and transfer function. So that is a pictorial representation of block diagram. Coming to second one, it can be used to represent linear as well as non-linear systems. Okay, so we know what is a linear system and what is a non-linear system. So we can use this block diagram representation can be used for both linear as well as non-linear systems. Okay, block diagram, signal flow graph, it can be used to represent only for linear systems. Okay, so here this is applicable only for the linear systems. Input multiplied with output, input multiplied with transfer function, you will get output that is in linear fashion. Okay, gain is always a linear quantity. Okay, so you will have a relation, so output which is equal to input multiplied with gain. So whereas in block diagram, so we can represent nonlinear quantities also. Okay, next coming to the third one, the no direct formula is available to obtain the overall transfer function of the system. So one step by step we have to follow in block diagram reduction technique. So first, either we can merge the blocks, or we can eliminate the parallel paths, or we can eliminate the feedbacks. Depends upon the convenience. We can start at any point. So to get to understand easily, what I have said is initially first step we have to eliminate the cascade things. The next step eliminating the parallel paths. Next step we have to eliminate feedbacks. Okay, like that I have told, but we can follow. There is no particular procedure to get the overall transfer function. So we can eliminate, initially we can eliminate all the feedback loops. Later we can join all the blocks. Later we can eliminate parallel paths. Like that we can follow any of the steps to get the overall transfer function. But in case of Mason's gain formula or signal flow graph, Mason's gain formula is available to find out the overall transfer function. In a single step, you will get a overall transfer function. So here in signal flow graph, block diagram is not a systematic procedure. There is no systematic procedure for block diagram to reduce the blocks. Okay. Coming to fourth one, step-by-step procedure is to be followed to find out the transfer function. So one after the other, we have to eliminate all the blocks, finally to get a transfer function. So in case of signal flow graphs, transfer function can be obtained in a single step. Just once we calculated all the loops, once we calculate the gains, identified the forward paths, and the next individual loops, next two non-touching loops, three non-touching loops, like that. If we identify all these things directly in a single step, we'll get the answer, overall transfer function. Okay, in block diagram, it is not a systematic method, whereas for a signal flow graph, even it is a complex signal flow graph or a simple signal flow graph, we have to follow these steps. We have to identify the forward paths, we have to identify the loops, we have to identify the non-touching loops, finally apply the Mason's gain formula to get the solution. Okay, so it is a systematic procedure. Coming to block diagram, it indicates more realistically the signal flow graph of the system than the original system itself. So it is very correct. So block diagram, it gives the more realistically the signal flow of the system. For example, already we have learned about the field wind transfer function model of a or block diagram model of a DC motor, armature controlled DC motor. We have already obtained the transfer function for it. Okay, there the field winding is represented with the one block. Similarly, armature winding is represented with a one more block. Mechanical system is represented by one more block. Okay, so like that we have obtained the transfer functions for individual circuits. Okay, present inside a single motor. So physical system is a single motor, but there is no realistic representation. The signal flow graphs can be analyzed. Signals can be analyzed at the flow of current, generation of quantities, maybe a torque or current. So everything can be analyzed more realistically in block diagram representation. So what is the output of a field winding? What is the output of an armature winding? So what is the input for a mechanical system? Okay, like that it gives the more realistic information in block diagram. Okay, so that's why block diagram is used to represent a complex systems. Coming to signal flow graph, it consists of more rigid mathematical rules than the block diagram. More rigid mathematical rules than the block diagram. So it gives only a part. Okay, it also gives the more realistic value, but when compared to block diagram, so it is it gives less information, but okay. Okay, number 275. If you have any doubts, you can raise 20B85A0275. Unmute your mic. Otherwise, if you have any doubts, you can ask. 275. But 275. Unmute your mic. Or if you have any doubts, you can raise. Okay, so that is about comparison. And finally, for a given system, the block diagram is not unique. Okay, made dissimilar and unrelated systems can be represented by the same block diagram. Okay, so for a given system, if we take a motor, a DC motor, the block diagram is not unique. So block diagram means, so I can represent the field winding and armature winding combinedly. We can frame a single block. 1%, it shows separately field winding for a single block and armature winding we can represent with another block. And one more person, he represents the resistance of the armature winding is represented by a single block. Inductance of the armature winding is represented with a single block. Flux generated inside that one can be represented with some more blocks. Like that, it can be represented. So for a same system, the block diagram representation is not unique. Okay. So it is not the unique value. Similarly, for a signal flow graph, it is also not unique. Finally, we have to get a transfer function model as a unique one, but intermediate models, that means the signal flow graph model or a block diagram representation, so that can be varied from person to person. Okay. So I have represented some armature winding one number of blocks, whereas in case of field winding and that can be represented with a single block. So automatically the appearance, it changes. The block diagram representation is not unique for the same system. Okay, similarly for signal flow graph. Okay. Number 248, 20B8, 5A0, 248. Please unmute your mic. Okay. Next, try to solve this example. So obtain the transfer function of the control system whose block diagram is shown in figure. So block diagram reduction technique and signal flow graph. If we use both techniques, we have to get the same model. This problem we have already obtained. We have obtained the transfer function using block diagram technique. In the previous classes, we have calculated transfer function for this block diagram. That's why I have selected this one. Using signal flow graph, again, we have to obtain the same transfer function. Okay. So try to solve at home. So this is, so note down this figure. First of all, and first step is finding, we have to find out the junctions. At first junction, second junction, third junction. Okay, this is fourth one, this is fifth one, and final output is C, input is. So signal starts from here and reaches to this one. This is an input node, or C is an output node. So intermediate, these 1, 2, 3, everything are called as mixed nodes. And also one more node, that is at 6. Okay. So first we have to identify the nodes. Later we can directly represent with the gains. Similarly, from here to here G1, from here to here unit value, from here to here it is unit value, from here to here it is G2, and one more G3 in the same direction. So from here to here again 1 unit value. So feedback. So positive feedback here it is. So plus H1. Okay. So from 5 to 6 here again unit value. Now from here second to 6th point it is minus H2. Since it is negative feedback, so we have to represent with -2. So from this first junction to sixth junction. Again, this is a forward path with a negative sign. So minus G, I think it is 4. So that completes simple signal flow graph. Construction of signal flow graph using block diagram. So identification of nodes is very important. Once we identify the nodes, we can directly from the signal flow graph. So this is the signal flow graph. Okay. So this is the signal flow graph from R to this. Okay, from R to this, and then again x1 to x2, x2 to x1, and simply we will get from here to here it is minus h2. So signal flow graph representation. Okay. So note down these figures. So once you obtain the signal flow graph, next step is this is the signal flow graph. Again, I have shown identification of loops, forward paths, and individual loop, first forward paths, next individual loops, next non-touching loops. Okay, so these are the forward paths. So first forward path, if we observe, that is the first one forward path is the signal is flowing from input node to output node. This gives the first forward path. So R to x1, x1 to x2, and this forward path gain. This is called. This is what I have represented with gain GI. Okay, gain is represented with M1. Otherwise, we can represent with P1 or anything. Okay. In some textbooks, that is represented with M, and some textbooks it is represented with P, path gain. Okay. So first path gain is only G1, G2. Other quantities or unit values. That's why G1 into G2. So next, the second path. So simply, so we can consider the simply x1, x2, x3, x4, x5. With the other path, so from here to here, we have to follow the same, and we have to take the other direction to reach final out. That becomes the second forward path. First forward path is directly. So instead of G2, here we have obtained minus G3. So the path gain, either P2 or M2 we can take. Okay, path gain as minus G1, G3. Okay, are you able to follow that one? The next, third path. So can anybody identify the third path? What is the third path? So third path is with in this direction. So from here to here, the signal flows and it takes minus H2 and again minus H2, minus G4, minus H2 and finally reaches the out. This is the third path. Okay, the direction of the signal is in this direction. Here at this junction, at this node, that the signal can be taken in this direction, and again the direction of the signal follows minus H2 and finally it reaches to out. So that can be treated as third path T3. Okay, G1, first one is minus G4, minus H2, G1, G2 and so on. So finally we get the third one. Okay, next, fourth forward path. Is there any fourth forward path? Yes, it is also. So one more forward path is there. So that is from, again, it has to follow the same thing, same direction. So minus G4, minus H2, Up to x3 it takes same direction, and again it reaches the fourth. So we have to identify the forward paths. Four forward paths. Is there any other forward path? And again, in all these four, if I observe all these four, no node is traversed more than once. All the four paths, if we observe, no node is traversed more than once. So that first of all, we have to identify the paths. Okay, note down all these four paths. No need to write down this everything. Okay, simply write down the paths, four forward paths and its gains. Four forward path gains. Okay, next step is identification of loops. That is individual loops. Only there are two loops. Okay, so first loop is, see, this is not a loop. The starting point and ending point should be the same, and no node is traversed more than once. So it is not possible. For this, it is possible. The signal is traveling in this direction, G1, G2, G3 up to this node, and again coming back to the same node. So that completes node 1. G1, G2, okay, H1 and minus H2. So this is not minus. Okay, finally you will get the loop gain. Loop gain is going to be minus G1, G2, H1. Okay, that is the loop gain. And one more gain loop, we can take this as another loop. The second one. Second loop is G1 minus G3 unit value and H1 minus H2. So we can consider that as loop 2. There is no other loops. Even though if we observe the graph, only two loops we can identify. Next step is identification of non-touching loops. So non-touching loops means, again, there is no non-touching loops in this case, because those two are in contact at this junction and at this junction. So these two loops are in touch with each other. So there is no question of non-touching loops. So directly we can determine the determination of the signal flow graph delta value. Delta is equal to 1 minus individual loops plus 2 non-touching loops minus 3 non-touching loops. That is the formula. So first, to just delta 1 minus of, write down the individual loops. You will get delta value, determinant of the graph. Now again, we have to find out delta 1, delta 2, delta 3, delta 4. So because there are 4 forward paths, so a number of forward paths is 4. That's why we have to find out delta 1, delta 2, delta 3, and the delta 4. So delta 1 is, how to find out delta 1? So this is first forward path. Okay, we have assumed 1 minus individual loops which are not in contact with this first forward path. So first loop this is, second loop is this one. Okay, so both loops are in contact with first forward path. So delta 1 becomes unit value. Okay, so that is first one. So how to find out delta 2? Delta 2 is, again we have to consider this second forward path. Second forward path is this one. Again 1 minus loops which are not in contact with second forward path. So again these two loops are in contact with this one, this forward path. Okay, loop 1 and loop 2. This is loop 1 and loop 2. Okay, these two are in contact again at the same point. So that's why put 0. Delta 2 is also 1 minus 0. Delta 2 is also 1 unit value. Delta 3. Delta 3 means again 1 minus loops which are not in contact with the third forward path. Third forward path is this one. Again, these two loops are in contact at this point, same points. So again becomes unit value. Delta 4 is equal to 1 minus loops which are not in contact with fourth forward path. Again, fourth forward path is the same, this path. So this is the fourth forward path. Again, at the same points, they are in contact. So put 0. Okay, if any of the loop is not in contact with this forward path, in that case, we have to put that loop value, loop gain value in this brackets. Okay, is it clear? So delta 1 is 0, delta 1 is unit value, delta 2, delta 3, delta 4, everything is unit values. Now directly substitute these values in figure. So this is our Mason's gain formula. M1 delta 1, M2 delta 2, M3 delta 3, M4 delta 4 by delta. Directly substitute, you will get transfer function. Okay. Is it clear? Anybody is having doubts? Directly we can obtain transfer function model from the given signal flow graph. Even though if we use block diagram reduction technique, we have to get the same transfer function. Final transfer function is same. Okay, for a physical system, the block diagram can be represented in different forms. Similarly, signal flow graphs can be represented in different forms. It is not unique. Okay, but whereas the final transfer function is same. Okay, either if we use Laplace transforms to get transfer function from the mathematical model. So finally, you have to get the same model. Okay. Any doubts? So that completes signal flow graph. Now we are going to start the next chapter. Any doubts up to this topic? If you have any doubts, you can ask. Now we have obtained that model, a transfer function model. In this unit, we are going to learn about the response of the system, time response of the system. So with respect to time, what is its output? So we just write in the first unit, we have obtained the mathematical model for a given system. Now our aim is to find out the output from that mathematical model. Okay, in this chapter we are going to learn about the time response analysis. So what is the time response? So the name itself shows the time response C of t, that means with respect to time, is the variation of output with respect to time. What is the output with respect to time? So in a graphical fashion, at each and every instant of time, if we calculate its output, that gives the response. With respect to time, what is the output? What is its output? Okay, so that is nothing but the time response. The part of the time response that goes to zero after a large interval of time is called a transient response. And the part of the time that remains after the transient response is called as a steady state response. This is the time response, means the total time response or the total response of a system can be divided into two parts. It is a combination of two responses. The total response is a combination of two responses. One is a transient response, the other one is steady state response. Still now in networks, okay, electrical circuits 1 and 2, we have studied only for steady state response 230 volts. Okay, that is a steady state value. Okay, so at any instant of time, if we calculate, if we measure the quantity, that is 230. Okay, with respect to time, that is always 230. That means it reaches to a steady state value. So before it reaches to a steady state value, one more response is there, that is called as a transient response. That is very short interval of time, maybe a microseconds or milliseconds. Okay, there the quantities are not 230. Okay, even though the input quantity is 230, but it shows something around 400 or 270 or 300. The values may be entirely different. Okay, so we have to study the response as in the response in transient state as well as steady state. Once the system can withstand, okay, for transient period, the system can automatically withstand for steady state response. Okay, so whenever some input is given to a system, so the output is, so initially a transient response. After a certain time, the transients will die off and it reaches to a steady state value. Okay, so something like this. Suddenly, if we close a switch, initially the voltage across the switches, there is no current passing through the switch, it is kept open. So only zero, the response, there is no response, the voltage is zero. Immediately whenever something is added, some switch is closed to the system or to the circuit, it appears some 230 volts is suddenly appears across the circuit. So that means it has to reach from 0 to 230 volts within no time. Okay, but it takes, because of some capacitance and inductance, that is energy storing elements present inside the circuit, it takes certain time to reach 230 volts. Before it reaches to 230 volts, it reaches to a maximum of 400 volts or more than that in some cases. Okay, maybe 1000 volts. And again, finally, after certain time, it reaches to 230 volts. So that period is called as transient period. This transient period dies after certain time. So the part of the response which remains after the transient period is called as steady state response. Okay, so we have to study the response, the complete response of the system. The mathematically that can be represented with C of t is equal to the transient period plus steady state period. So for example, if we take something like this, okay, input is R of t. So initially at the 0 time, before 0, there is the switch is kept open, there is no output. Immediately at 0, t is equal to 0 time, the switch is closed. Here the input value is unit value 1. Okay, so even though the immediately after the switch is closed, the response, if we observe, it is suddenly raised to 1.5. Okay, So 1.5 means it is initial, it is 1, but input is 1, but it is raised to 1.5. Again, after suddenly it comes down to 1.7, and again it is raised to 1.2, and finally after certain time it reaches to unit value. So this period is called as transient period, where this is called peak overshoots. These are called undershoots. So where the peak overshoots and undershoots takes place, and finally it settles to the value that is called as steady state period. Okay, steady state response and transient response. Mathematically, C of t is equal to, that can be represented in this fashion. Now, same thing what I have said, transient response. After applying the input to the control system, the output takes certain time to reach steady state. So the output will be transient till it goes to steady state. Therefore, the response of the control system during the transient state is known as transient response. This period is called transient response. In transient response, there is overshoots, there are overshoots, undershoots, and time taken to reach steady state value is called as that is settling time. Okay, to settle, that is called settling time. Time taken to reach this maximum value, unit value, so that is called as rise time. There are so many quantities to represent this response. Okay, later we can discuss about that rise time and the shoot and all. So now the complete response is a combination of two responses. One is transient response, the other one is steady state response. Okay, so the transient response will be 0 for a large value of t. Ideally, this value t is infinity, and practically it is 5 time constants for any system, for any practical system, and that is up to 5 time constants. So the transient period will be up to 5 time constants. After that, it reaches to steady state value. So mathematically, that is represented with a limit t tends to infinity. This is the mathematical form. Limit t tends to infinity. C of t is equal to 0. Okay, so that is the transient response dies after certain time. Okay, so after certain time, the transient period dies off. Mathematically, the transient response, that is, can be represented in this fashion. Limit t tends to infinity. T transient of t is equal to 0. Okay. Now coming to steady state response. The part of the time response that remains even after the transient response has 0 value for a large value of t is known as steady state response. So that is whatever may be the quantity left out after the transients are died is called as steady state response. Now, how to get this response? Time response can be obtained by solving the differential equations governing the system. That is one way of getting response. Till now, we have studied about the time response of the system, C of t. It is a combination of two terms, that is transient response and steady state. Now, how to get this output? Okay, so we have mathematical model, that is mathematical equations in differential equation form. Okay, so directly by solving that differential equations, you will get the response output C of t. That is one way of getting. That means we have already studied in our mathematics 2, 3, and so on. Okay, mathematics 2, 3, solving the differential equations, homogeneous equations, non-homogeneous equations, homogeneous equations with the so finally we have to get the solution as a complementary function, particular integral, everything you will get. Okay, so directly solving, applying the differential solution methods, so we can get the response. That is one way of getting solution. Next, alternatively, C of t can be obtained by transfer function of the system for a given transfer function from the transfer function model. Once we get the transfer function model, either from the block diagram or from the signal flow graph or directly from the mathematical equations. Okay, if we have transfer function model, okay, and the given input is known for a given known input, directly transfer function is nothing but multiplied with, so C of s is equal to transfer function T of s multiplied with R of s. R of s is input. Output is equal to input multiplied with transfer function. So directly by taking inverse Laplace, you will get output. Okay, same thing what I have taken here. The closed loop transfer function C of s by R of s is equal to G by 1 plus GH. That is a well-known simple system. So this was the system, a simple system with forward transfer function gain is G and output is C of s. This is standard system. Okay, so here one takeoff point with negative feedback, H of s takeoff. This is negative. So for this system, the closed loop transfer function is C of s by R of s is equal to G by 1 plus GH. So this is our transfer function. So that can be represented with M of s. Okay. Response in S domain is equal to C of s is equal to multiplied with M of s multiplied with R of s. Just now what I have told, taking the Laplace, inverse Laplace, if we apply, the response of the system C of t, the total response of the system is equal to Laplace inverse of C of s or Laplace inverse of these two terms. For a given input, so input is known value, multiply with transfer function, taking Laplace transfer, inverse Laplace. That means, so we have to apply partial fractions here and apply Laplace inverse, you will get direct solution. Okay, in this chapter, we are going to solve this one, this part. So finding C of s, the entire chapter deals with C of s. Try to remember this formula, that's it. C of s is equal to inverse Laplace of C of t is equal to inverse Laplace of R of s into M of s. For different inputs, for the same system, if the input is different, you will get the different response. For the same input, if the system is different, okay, the response is going to change. Okay, the response mainly depends upon input as well as system. That we have to remember. Okay. Now, standard test signals. Here, what we are dealing with, this first term, first case, we have to study different types of inputs. Okay, to get this response output. So first, our aim is to study system is same if the input is different inputs. If I apply different inputs for the same system, what is its response? In case 2, for the same system, for the same input, if the order of the system is changed, that means order means maybe a first order system or a second order system, that means the transfer function is changed. what is its output. That we are going to deal in this chapter. Okay, is it clear? Now, test signals. The knowledge of the input signal is required to predict the response of the system. The compulsory to predict the output is not, we don't know the output value. If we want to predict the output, the knowledge of the input is very essential. Okay, so these inputs, the characteristics of the actual input signal are sudden shock, suddenly that can be raised, sudden shock, a sudden change, a constant velocity, and a constant acceleration. Generally, the inputs are of combination of these things. Any practical input. So practical input may be something like this. Okay, it is a combination of a sudden shock or a sudden change or some constant velocity or some constant acceleration. That means sudden shock means it is suddenly it is raised to a peak value. Okay, so otherwise a sudden change, suddenly it is at a small interval of time with respect to time, within no time it is reached to maximum value, infinite value. So here within no time it is reached to a certain value. Okay, a constant velocity or like that, the quantity may linearly increasing, or it may be something in parabolic fashion. So it is sharply, it is increasing gradually. Okay, so any practical input is a combination of these standard inputs. If any system is able to withstand for a standard inputs, that means standard test signals. Okay, this is our system. So the output can withstand for any practical input. Okay, so hence the test signals are resembles the characteristics that are used input signals to predict the performance of the system, to predict the output of the system. Okay, so for a standard system M of S, so if we can find out the response for these signals, the system can be withstand or the practical output can be calculated for any practical input. So here it is. Now, so here we have to find out, once we get the mathematical model for this input and mathematical model for our system, directly we can apply Laplace transforms to get the response. We can predict the response of the system. Okay, so we'll discuss the standard signals in the next class. If you have any doubts, you can raise, otherwise we can stop here. Any doubts regarding today's session?